Now, the first thing we want to do is we want to build an objective function that calculates the Sharpe ratio for a given weight. Yeah, because that's what we want to optimize. We want to put in the weights, get the Sharpe ratio out. So how do we do this? We're basically just calling this function f, and our input will be the weights. So that's what we get. And so what we can do then now is we could do something like reds, and then we multiply them with the weight. And then instead of mean, we have to calculate the sum. And so obviously we don't plot this. We just call this, say, R. So we multiply this with the weights and the sum. And then what we do is we go S equals R dot mean divided by R dot STD times 16, right? And then we return S. Okay, so now what we can do is we can actually do this F, and then we just put in some weights. So we could do 0.33, 0.33. So they all have approximately the same weight. And then our Sharpe ratio will be 0.56. So if they're equally weighted, it will be 0.56. Now, what we can do is we can use this, say, as a starting weight. We could do something like W, So this is our initial weight, because we also need to supply some initial values as we did before with this other function. So let's just go, W is this, yeah? And then we go minimize F and W, yeah? So we've got F here, it's our function, we've got our reds that we produced here. So let's run this again, and then we minimize, and there we go. These are your X values here. And then you've got your function value, which is, see this? Minus 0.69, but there's a problem here. What's the problem?
What I was thinking of is that it's going for like the minimum, right?
Correct. That's absolutely right. We actually need to do this minus. We need to put a minus sign here because we want to minimize. We want to actually find a maximum. And right now it looks for the minimum. So we need to run this again. So we get a negative function value, which is actually, it's just a negative value here. But you can see here, we get X 0.49, 0.06, and 0.34. These are our values, right? And the actual Sharpe ratio that we end up with is 0.69. So I think it's actually a teeny weeny little bit higher than what we had before, correct? So what we can do now is we can do this res equals this. So now we can take our function again, and we can do f of res dot x. And then, of course, we need to do the negative of that. And that's our function value. Now, the other thing we can do is we can actually print this. So we've got our returns here. We could do reds dot and then multiply this by res of x. And then we need to do the sum. X is equals 1. Yeah. Dot cumulative sum dot plot. And that's basically the curve of the resulting optimized strategy. Yeah. So let's just do this again. And instead, we plot the original strategy, the original W, which was, so we multiplied by W, which was the equal weights. And there you go. See, this is the original strategy. It actually returns a little bit more, but you can see it's actually a lot more volatile. So the Sharpe ratio is a lot worse. Yeah. So what we've done here is we basically build a much safer strategy altogether.